Alright, so let's take a look at the June 2011 Unit 5 paper. So we've got 23392U, and it's going to decay through beta minus. So beta minus causes the proton number to increase because a neutron is turned into a proton. So that means it would have originally been 91 in there, but it doesn't cause the nucleon number to change, so that's still going to be 233. But in addition to beta minus, you would get electron neutrino form to conserve lepton number. Alright, so two other nuclei can also decay into 23392U. We've got a beta plus and alpha emission. So during beta plus, a proton is turned into a neutron, so P is going to be 93 and 140, because what's going to happen is a proton is going to turn into a neutron, so proton number goes down and then neutron number goes up. During alpha, you lose 2 protons, so the proton number is going to be 94 in the originally, and you lose 2 neutrons, so it's going to be 143. So that means Q is going to be up here on your diagram. Okay, so let's move on. So a typical reaction is represented like this. Calculate the number of neutrons. So essentially this is a baryon conservation. So on the left we have 234 baryons, and on the right we have 91 plus 139 plus x baryons, and those two must be equal to each other, so x is going to be 234 minus 91 minus 139, so let's do that. 234 minus 91 minus 139, which is equal to 4 neutrons. So to conserve baryon number you need 4 neutrons. Calculate the energy released in mega electron volts in the fission reaction above. Okay, so essentially what we need to do is work out the change in binding energy. So I just had a look at the mark scheme for this question, and frankly the answer is total and utter rubbish, because they get you to add together the masses on each side and work out the difference in mass. That is ridiculous, so I'm going to show you how to do this properly, not by what the mark scheme says. So the binding energy initially is going to be, that's essentially how many you should have. This is how many you have afterwards. So that's your mass defect, so times by 9.31. So 233 minus 232.98915 gives you the mass defect, so times 931 gives you total binding energy of 10.0905 ... MeV. So the binding energy afterwards is going to be 91 minus plus 139 minus 138, and then all of that multiplied by 931, so that's going to get, so 91 minus 90.90368 plus 139 minus 138.87810, which gives you 0.21 times 931, gives you 20362. Therefore, the change in binding energy, which is the energy release, is going to be that minus 10.0905, which is equal to 193 mega electron volts, because that's the change in binding energy. Neutrons don't have any binding energy because they're not bound to anything. So be very careful with this question. What they've done in the mark scheme is ridiculous and doesn't make any sense, so be very careful. Okay, let's move on. So the first artificially produced isotope, phosphorus, was formed by bombarding an aluminium isotope with an alpha particle. Complete the equation by identifying the missing particle. Okay, so total nucleon number on the left is 31. Once you take into account the aluminium and the alpha, so we need 1 on the right hand side. Total number of charged particles on the left is 15. And on the right hand side is 15, so whatever it is must be neutral there, which means it's a neutron. Okay. For the reaction to take place, the alpha particle must become within a distance d of the centre of the aluminium nucleus. Calculate d if the reaction occurs when the alpha particle is given an initial kinetic energy of at least 2.18 times 10 to the minus 12 joules. And we've got the equation for potential energy. So this is the distance of closest approach question. So essentially what we're going to be doing is equating this expression here. So d is going to be the charge on the, what is it? It's an aluminium, so it's going to be 13 times by 2 times 1.60 times 10 to the minus 19 squared, because it's in both terms involved in the expression, and that's going to be 4 pi E0 times by 2.18 times 10 to the minus 12, which is equal to 13 times 2 times 1.60 times 10 to the minus 19 all squared, divided by 4 times pi times 8.85 times 10 to the minus 12, and also divided by 2.18 times 10 to the power of minus 12, which comes out as 2.745 times 10 minus 15, which is approximately 2. What have we got? It's going to be 3 significant figures because that's the information we've been given in the question. 10 to the minus 15 meters, or 2.75 femtometers if you like. Alright, so then it wants us to sketch a binding energy per nucleon against nucleon number for naturally occurring nuclides, giving values and a unit to the binding energy per nucleon. So we typically deal with this stuff in this scale in mega electron volts, so that's going to be your binding energy per nucleon on your axis, and we typically hit a maximum value of about 8.5, somewhere around there, at around 56, which is going to be somewhere, let's make the whole thing 10, so that's going to be 8, so it's going to be sort of hit a maximum value up there, because it's 56, so it's going to essentially go, and then we're going to have quite a shallow descent over the other side, so something along the lines of this. You don't want it to be too steep or it will drop too dramatically. It should be quite a shallow decrease at this point. Okay, use the graph to explain how energy is released when some nuclides undergo fission and when some undergo fusion. So essentially, you get energy released when binding energy per nucleon is increased. For fission, a larger nucleus forms 2 or more daughters, and that happens to right of peak, for fusion to essentially merge to form one overall nucleus, and that's to the left of the peak. And then, so it's stable at the peak position on your curve. So that's what it's going to be looking for then. So the condition under which energy is released is this one here, and the different possible ways it goes about it are, if it's to the right along here, it undergoes fission to increase its binding energy per nucleon, and if it goes fusion, it's down here in the fusion zone to increase its binding energy per nucleon, which is what it's always trying to do. Okay, so moving on to some thermal stuff. You've got an electric heater. It's holding 100 grams of ice at a temperature of -14, and it supplies energy at a rate of 98 joules per second. After an interval of 30 seconds, all the ice has reached a temperature of 0 degrees. Calculate the specific heat capacity of ice. So the energy delivered is going to be 98 times by 30, which is 98 times 30. Total energy of 2940 joules. The specific heat capacity is Q over M delta T, which is 2940, which is Q. 0.1 kilograms times by 14, which is a change in temperature. So divided by 0.1 times 14 comes out at 2.1 times 10 to the 3 joules per kilogram per Kelvin. So the final temperature of the water formed when the heat is left on for a further 500 seconds is about 40 degrees. So the total energy supplied is going to be the times, which is 500 times 98. 500 times 98, which is 49000 joules. Amount of energy it's going to take to melt is going to be ml, which is going to be 0.1 times 3.3 times 10 to the 5, which is so 0.1 times 2.3 10 to the power 5, which is 33,000. So delta T is going to be Q over MC, which is going to be 49,000 minus 33,000, so that's the heat energy left over, and 0.1 times 4200. Okay, so 49,000 minus the answer from the previous question, divided by 0.1, divided by 4200, which is 38.09, which is approximately 40 degrees C. It started at 0, so that's what it's going to finish at. The whole procedure is repeated in an uninsulated container in a room at a temperature of 25 degrees Celsius. So explain whether the final temperature of the water formed would be higher or lower than calculated in part B. So for the majority of the time, the system is below 25 degrees, so you're going to get heat transferred from surroundings. So then you're going to get heat supplied is increased because you're getting it from both the heater and from the surroundings. So then you should, in theory, reach a higher temperature, because it's only for the last little bit that it's actually hotter than the surroundings and it's losing energy. So most of all, you're actually going to be gaining energy from your surroundings. Okay, a fixed mass of ideal gas at low temperature is trapped in a container at constant pressure. Gas is then heated and the volume of the water changes so that the pressure stays at 1 times 10 to the 5. When the gas reaches a temperature of 0 degrees, the volume is 2.2 times 10 to the minus 3, to show this on a graph. So 0 degrees, it should go through 2.2, which is somewhere around there. It's not brilliantly plotted there. And when it gets to the volume is 0, it should be at minus 273, which will be about somewhere around here. It's a little difficult to do with a stylus, and it's going to be a straight line graph, so I'll do the best I can on my computer screen. So something a little bit like that. Okay, calculate the number of moles of gas present in the container. So if we want the number of moles of gas, we can use PV equals nRT, because then N is PV over RT, and our pressure was 1 times 10 to the 5. Our volume was 2.2 times 10 to the minus 3, divided by the gas constant, which is 8.31, and that's at 0 degrees, so 273 Kelvin, so 1 times 10 to the 5, minus 2.2 times 10 to the minus 3, divided by 8.31, divided by 273, gives 0.09697 dot, so that's going to be 9.7 times 10 to the minus 2 moles there. Okay. Calculate the average kinetic energy of a molecule when the gas is at a temperature of 50 degrees C. So the kinetic energy is for an individual molecule is 3 over 2 kT. So it's going to be 3 over 2 times 1.38 times 10 to the minus 23 times by 273 plus 50.0. So 273 plus 50 is 323 times 1.38 times 10 to the power minus 23 times by 3 divided by 2 gives you 6.6861 times 10 to the minus 21. So we need to give this a 3 significant figures because that's what all the data in the question is. So it's going to be 6.69 times 10 to the minus 21 joules. Calculate the total internal energy. So we're going to need to work out how many molecules there are. So from the previous question, we know the number of moles. 97 times 6.02 times 10 to the 23 times by 6.6. What was it? 8 times 10 to the minus 21. So let's multiply those. Times 6.02 times 10 to the power of 23 times 0.097 gives you about 390 joules of energy. By considering the motion of the molecules, explain how a gas exerts a pressure and why the volume of the container must change if pressure is to remain constant as temperature increases. Okay, so the first thing is pressure is the force divided by the area of a container, and a force is rate of change of momentum, like this, and then there's the time between collisions here. So if the temperature increases, that means the kinetic energy of the molecules increases, which means the momentum of the molecules increases. So that would mean your change in momentum, or your top line, has increased. So that's going to result in an increase in pressure on the container. So what we need is something to counteract that. If volume increases, the cross-sectional area increases, so that can help offset the increase in momentum, and your time between collisions increases. So if you increase the volume, the time between collision increases and the area increases. So what you end up with is that the pressure, yes, your momentum increases because of the increase in temperature, but because you've increased the area and because you've increased the time between collisions, you can get a constant pressure as a result of that if those increases result in no change there. So obviously you'd need to write this fully in words, but these are the key stages you'd go through in your explanation for this question. And that concludes this assessment.